Okay, hi everybody. Okay, now we're going to start a new topic in this module, module 7, which is the sample data system models. Now that we have reviewed the continuous systems models, we're going to move on to looking at the discrete and the sample data models. So what we're going to be covering in this topic, we're going to be looking at sampling and reconstruction, and we're going to be looking at analog to digital conversion. We're going to look at the sampler, at aliasing. Then we're going to look at digital to analog conversion. We're going to look at zero order hold and first order hold. And then we're going to look briefly at the circuit implementation, and we're going to look at sample rate selection. Okay, so let's look at a sample data system that we have the block diagram for here. So if you look at the sample data system, we have an input, a command that is continuous in time. We're going to take that command. We're going to take the output of the system, assuming that output of the system is continuous. We're going to subtract them, and that's going to give me my error signal, E of t. Now what I want to do is I want to be able to control my plant using a digital controller. So therefore, I'm going to use a computer to control my plant. I'm going to take this error signal, I'm going to take it and convert it from analog to digital, and that will give me E of k, the output of the analog to digital converter. Now this E of k is going to be used to drive as an input to my controller C of z. So C of z, the controller, the compensator, the filter, is going to be driven by the error signal E of k, the discrete time error signal E of k, to generate an output that is U of k. Now the output of this filter, or the controller that we designed, has to be converted back to an analog signal in order to be able to input it to the plant. So therefore we're going to take U of k, we're going to put it through a digital to analog converter. That's going to give me U bar of t, and that is going to be the signal that's going to drive the plant, that is applied to my plant. And then I'm going to have my output, Y of t, that is fed back in order to be compared to the command R of t and generate the error signal. So what we're going to be doing in this module and future modules is we're going to be looking at this block, the analog to digital converter, and then we're going to be looking at the analog to digital converter and the digital to analog converters. Okay, so let's start with the analog This is A, we called it, and then 1. We're going to start with the analog to digital conversion. And let's start with the ideal sampler. So if I look at the analog to digital conversion, I can represent that conceptually by an ideal sampler. The analog to digital conversion can be represented conceptually by the ideal sampler. What is the ideal sampler going to look like? It's going to look like a switch that will turn on every t seconds in order to obtain a sample. So on the left side, I have the continuous time signal. And let's say we have a signal that is E of t from the previous block diagram. And I'm going to be sampling this signal, the continuous time signal E of t, every t second to generate a discrete time signal that we call E of k. And k is equal to 0, 1, 2, 3, 4, all the way to infinity. So therefore, this input E of t is sampled at discrete time instance that is 0, t, 2t, 3t, all the way to kt. What do we call this t? We call it the sampling time or the sampling period, where t is the sample period and k is a positive integer. Okay, so therefore I can represent this sampler as E of k equal to the continuous time signal E of t evaluated at t equal to k multiplied by t. So therefore I'm going to have E of 0 equal E when t is equal to 0 multiplied by t, therefore E of 0. E of 1 is going to equal to E at t equal 1 multiplied by capital T, therefore it's equal E of capital T, and so on and so forth. Okay, I can illustrate this relationship by the figure here. If I take a continuous time signal and let's say we have my continuous time signal looks something like this. So this is my E of t and this is my continuous time signal axis t. I'm sampling this signal every t seconds. So at 0, at t, at 2t, at 3t, I'm going to be taking a sample to generate the sample signal E of k, which is going to be only having values at these sampling instances. And this is k, this is 0, 1, 2, 3, and so on. So again, E of t, continuous time signal, E of k, discrete time signal, only defined at instances, which is k multiplied by t. And E of k is understood implicitly that it is equal to, E of k is equal to E when t is equal to k multiplied by t. So E of k is equal to E of k multiplied by t. Okay. Now the question that we're going to ask, what do we have to observe when we sample the signal like this in order to minimize the information that is lost? So as you can see, when I have the samples of the signal E of k, I am only taking the values, I only have the values of the signal at finite instances in time, only at discrete instances in time. What is it that we have to observe in order to minimize the information that we're going to lose? So therefore, if we look at the sampling process, the sampling process can lead to loss of information. And there are two reasons why we are losing information. So let's look at these two cases and illustrate how information is lost. Let's look what happens if we choose the sampling period t to be too large. If the sampling period t is too large, then what might happen, we might miss some information regarding the transient response of the signal. We miss information regarding the transient response of the signal. What does that mean? Let's look at this example. Let's say we have my signal that I'm sampling, E of t, looked something like this. So this is my continuous time signal, E of t. So what happens, of course, if you look at this response, we have an overshoot and we have some oscillation. And what we want is we want to capture all these dynamics, all this transient response. But what happens if we sample the signal and we chose the sampling period to be very large? So I sampled such that I'm taking a sample here. This is my sampling time. And this is another sample at 2t, another sample at 3t. Then the samples that I'm going to be getting that will be generating E of t is going to look something like this: a 0, whatever this value is, whatever this value is, whatever this value is. So what happened in this case? As you can see here, if I look at the samples that I've taken, I would have missed all this transient response. So if I chosen my sampling time, my sampling period t to be large, then E of k will have no information regarding the high frequency ripples that I'm seeing in E of t. So this is t, 2t, 3t. So here in this case, since t is large, actually let's make it numeric and just make this 1 second, 2 seconds, 3 seconds, and make this at 1, at 2, at 3. So this is 3 seconds, and we're going to assume that the sampling period t is equal to 1 second. So again, since we chose t to be large, we are missing all the information about the transient response and all the ripples that are happening in the transient response. So this is one source of loss of information. If I have dynamics in the signal, or if I have variation in the signal that are not captured by the samples, then I will lose that information. Okay. And this will happen when I choose the sampling period to be very large. If I chose the sampling period here to be smaller, then I would have been taking samples like this, and I would have captured these ripples and this dynamic change that is happening in the response. Okay, so this is one source of loss that will happen because of the sampling. Now the second source of loss happens when we quantize the signals, the samples that we've taken. So what happens when we do the analog to digital conversion, we're going to take the samples from this signal, the continuous time signal, and we're going to convert them to a digital signal. So we're going to convert the magnitude of the signal to a discrete value. Now, because we are using a finite number of bits to represent the magnitude, the amplitude of the signal, there will be information that is lost. And this is the second source of loss. since sample data system systems are implemented using digital computers, the values of the discrete signals are restricted to a finite set of discrete values. So we call this quantization. When I take a sample of the signal, the continuous time E of t, whatever value here, it can have any value since it's continuous. However, if I have to store it on a computer, I have to select a certain number of bits to represent that value. And therefore, I'm going to have a finite set of discrete values that can be used to represent this value. And depending on the value that I'm sampling, that might result in a loss of information. And just to illustrate that, let's look at what happens, for instance, as an example. If we are using 12 bits analog to digital converter. A 12-bit analog to digital converter. And assume that the input signal that we are sampling can vary in range between 0 to 10 volt. Between 0 and 10 volt. So therefore, what I'm going to do, I'm going to take the 0 to 10 volt and divide them or represent them using a 12-bit. Now, if I have 12-bit to represent the data, I'm going to have 4096 levels that I can use to represent the data. And if I take the range between 0 and 10 volt and divide it equally, then I'm going to assign the value to each one of these levels. So therefore, if I have, for instance, E of k is equal to 0 volt, this is my input signal, or the sample that I capture from my signal, E of t, and it happens to be a 0 volt, I'm going to use 0, 0, 0, 0, since we have 12 bits, 0, 0, 0, 0, 0, 0, 0, 0, to represent this 0 volt. This is B0 all the way to B11. And this has an equivalent value of 0. If I have a value that is E of k equal to 2.442 millivolt, then I'm going to use 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 to represent this, and this is a decimal 1, and so on and so forth. If I multiply this by 2, I'm going to use 0, 0, 0, 0 all the way, and then 1, 0. And we keep adding this binary all the way till we get to E of k equal to 10 volts. Now this 10 volt is going to be represented by 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and this is going to be an equivalent 4095 in decimal. Okay, so again, I'm taking the range from 0 to 10 volt, and I'm dividing it into a discrete number of levels. And depending on the value of the signal, I'm going to assign it to the closest level to that value. And this is what quantization does. And I imagine everybody is probably familiar with that and have seen this. Okay, now what happens if I look at this, just to understand where the error comes from? What happens if I have a value that I sampled that is 0? We assign it as 0. If it is 2.44, we assign it a 1. Now what happens if I get a signal in the range between 0 and 2.44? I'm going to assign it, I'm going to round it to the lower value, which is a 0. And therefore, if the input is a 0, I'm assigning it a 0. If the input is between 0 and 2.44 millivolt, I'm still assigning it a 0. And that results in that loss of information. So here, since we are doing the quantization, if the input is in the range between 0 and less than 2.442 millivolt, it will be rounded to 0. Information is lost. And again, this is what we call, or this approximation is called quantization. This approximation is what we refer to as quantization. Why is this information lost? Because when I look at the output of this analog to digital converter and it tells me it is a 0, there's no way for me to know whether the input was a 0 or if it was 1 millivolt, because 1 millivolt will be also assigned a value of 0. Together? So again, if you look at a typical graph that represents this quantization, you're going to see something that might look something like this. This is a range. So this is my input value, and this is my output of the analog to digital converter. So what this says, if your input is between this value and this value, you're going to assign it a fixed value, which is this value here. If the input is between this range and this range, between this value and this value in this range, you're going to be assigning it a fixed value that is here. Now, once you assign it these discrete values, you have no way of knowing the actual value of your input signal. Okay. Now let's go back and look at the sampling process. So again, this analog to digital converter is gonna include two processes. One is sampling, and the second is the quantization. So this process is what we call quantization, which is taking the magnitude and assign it to a discrete finite set of values. Okay, so if I look at the sampling process, going back to the sampling process, we can consider the sampling process as modulation process. can be considered as a modulation process. In which a pulse train P of t multiplies a continuous time function. And in the previous example, that was E of t. And the result of this multiplication, we're gonna get the sampled function E star of t. What does that mean? So what we're gonna do is we're gonna model the modulation process as we're gonna model the sampling process as a modulation process. And what that means, I'm gonna take my input signal E of t and I'm gonna multiply it by a pulse train, P of t. The result of this multiplication is gonna give me E star of t, which is equal to E of t multiplied by P of t. Okay, what does this pulse train look like? This pulse train looks something like this. These are rectangular pulses, and this starts at 0. This one happens at t, 2t, 3t, etc. This is my P of t. Now this rectangle that I plotted here has a width that is equal to 1 over gamma. And it has a magnitude that is a gamma. Okay. So each pulse, so let me put an arrow here. Each pulse has duration that is equal to 1 over gamma, and it has an amplitude that is equal to gamma, and the time between pulses is equal to t. So I write it here, time between pulses is equal to t. Okay. Okay, so let's see what happens if I take a signal and I multiply it by this pulse train. So let's say, okay, let me start a new page, and before I lose these pages, let me copy paste these. Okay. So let's say we have a signal E of t that looks something like this. This is my signal E of t, and this is the time. Now what I'm going to do, I'm going to take this signal and I'm going to multiply it by this pulse train. Now, of course, somebody might have noticed that this pulse train each pulse has an area that is equal to 1. So if I look at each one of these pulses, the width is 1 over gamma, the amplitude is gamma. If I multiply them together, the area is equal to 1 over gamma by gamma, which is equal to 1. Okay. So what's going to happen if I take this impulse train and multiply it by E of t? I'm going to get a signal here. This is t. That's going to look something like this. Each one of these pulses is going to be scaled by the amplitude of E of t. So therefore, this pulse here is going to be scaled by the amplitude of E of t. This pulse here is going to be scaled by the amplitude at that time. This pulse here is going to be scaled to give me this. Pulse here is going to be scaled. The pulse here is going to be scaled. Okay, now this signal is E star of t. Make sense? I took this pulse train. Of course, this pulse is very, very narrow. So if you want to be accurate, this pulse train is going to change its value with the signal. But if it is very, very narrow, we can almost say this is a constant and it's equal to the signal at that instance in time. Okay, so again, for an ideal, if I look at consider the ideal sampler, the pulse width is much smaller than the sample period t. Which is 1 over gamma, is much smaller than the sample period t. And in the limit, if I take the limit when gamma goes to infinity, then 1 over gamma is going to go to 0. So in the limit, when gamma goes to infinity, 1 over gamma is going to go to 0. We can replace P of t with an impulse train. And that impulse train, we refer to it as a delta sub t. What does that mean? So if I look at these impulses that I have here, we said the width of this impulse is 1 over gamma. Magnitude is a gamma. And we said we want gamma to be very large. So 1 over gamma is very, very small. The pulse is very narrow. Now if I make gamma go to infinity, then 1 over gamma is going to become very, very narrow. And gamma, the magnitude is going to go to infinity. And in the limit, when gamma goes to infinity, that pulse is going to become an impulse. What does that mean? Now the pulse train is going to become an impulse train. And the way we represent this is with an impulse at t, an impulse every t second. This is t, this is an impulse 2t, 0, 3t, etc. This is the impulse train, delta t of t. Is that clear? Of course, this is the axis, so let me remove it so nobody gets it confused. So this impulse, what is the characteristic of this impulse, as we'll see in a second? The area of this impulse is still equal to a 1. Remember, the width is 1 over gamma, the height is gamma. If I multiply them together, gamma with gamma is going to cancel, the area is still equal to a 1. So therefore, I can represent this with something look like this, where this indicates the area of the impulse. And the impulse train has an area that is equal to a 1. 1 over gamma multiplied by gamma is equal to a 1. And we can represent this impulse train delta t of t is equal to the summation from n equals 0 to infinity delta of t minus n multiplied by capital T. I hope this notation is clear. What this means is I have a delta when n is equal to 0. I have a delta at t minus 0, which is at 0. When n is equal to 1, this is delta of t minus 1 multiplied by capital T, which means I have an impulse at t. And then when n is equal to 2, I have an impulse at 2t. Okay, where delta of t minus n multiplied by t is the unit impulse that occurs at t equal to n multiplied by t. Okay. Now this impulse train, or this impulse function or unit impulse, has two important properties. So let's look at the properties of the unit impulse function. Has many properties, but the two properties that we're interested in is what we mentioned before, is that the area, if I were to integrate delta of t dt, this area is equal to 1. It has a unit area. And again, we said the area is 1 over gamma multiplied by gamma. True, gamma is going to infinity, but 1 over gamma multiplied by gamma, they're going to cancel out and they're going to give me an area that is equal to a 1. The second property is the shifting property that tells me the integration from negative infinity to infinity, delta of t minus a multiplied by e of t dt is equal to e of a. And what that means, if I take this impulse and multiply it by any signal, the area is going to equal the value of that signal at that instant in time. So here, you can see it here. So if I come to this impulse, this pulse train, if I multiply this pulse by this magnitude, this pulse is going to scale by this magnitude. Now, if this was an impulse, then the area is going to get scaled by whatever this value of the signal, e at, for instance, e of t. Does that make sense? Or should we illustrate it more? So again, if I have an impulse, this impulse has an area of 1. If I multiply this impulse by any signal, so this signal, this is the time for this signal. If I multiply them together, then the area of this impulse, this point is a, because this impulse is happening at t equal to a. This impulse is going to multiply this signal when t is equal to a. So this signal is at this value here that I highlight, that I have the arrow pointing to, is equal to e of a. Now, if I multiply this impulse by this signal, this impulse is going to scale, the area is going to scale so that it is equal to e of a. Okay. So therefore, if I go back and look at the sampling process, we call the output of the sampler, we represent it as E star. So therefore, we can come here and say the sampled function E star of t can be represented by the following. I'm going to say E star of t is equal to delta, the impulse train of t, multiplied by E of t. I can also write this, since this is a summation, the impulse train. Again, this delta t is impulse train. So if I substitute for it, I can write this as the summation from n equals 0 to infinity E of t multiplied by delta of t minus n multiplied by t. And therefore, if I were to plot E star of t is going to be made up of impulses, and each impulse is going to have an area that is equal to the value of the signal at the time of the impulse. So this is E of t, E of 2t, and so on and so forth. So the area, the impulse, so this is t0 to t, the impulse at sample time t has impulse at sample time t has an area that is equal to E of t. Now we can represent it as an impulse with the value, or I can scale this impulse, the length of it, to represent the value of E of t. Does that make sense? So I can have all these impulses of the same height and just put the values E of t, E of tt, whatever these values are. Or I can scale these impulses to indicate the value of E of t. Okay. So this is the sampling process. Now, what might result from the sampling process, so let's going back to the topics we are covering. What might result from the sampling process is something that we call aliasing. So let's look at what aliasing is. Now, if you have studied signals and systems or digital signal processing, you're probably familiar with aliasing. But let's look at a quick example to illustrate what this aliasing is. So if I'm sampling a signal, and if the sample period t is too large, then it is possible for more than one signal to produce the same sequence E of k. What does that mean? Let's look at an example. So what I'm going to do, I'm going to plot two signals. The first signal looks something like this. It's a sinusoidal signal. And the second signal, look, let's plot it with blue, looks something like this. and so on, continues, and the other one continues. Now if you look at these two signals, it's apparent I have two sinusoidal signals. This signal is the lower frequency signal. Let's call it E2 of t equal to cosine omega t. Now if I look at the signal here, it is obvious that this signal, the other signal, has a frequency that is 3 times the first signal. E1 of t is equal to cosine 3 multiplied by wt. So one period of one period of the other corresponds to 3 periods of the other signal. So these are the two signals. E1 of t is a high frequency, has a frequency of 3, and another signal E2 that has a frequency, so the first frequency, sorry, has a frequency of 3 multiplied by omega, and the second one is just omega. Now what happens if I come here and sample this signal? And the way I'm going to sample this signal is that I'm going to come and take a sample here. So this is 0. I'm going to take a sample here. 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 What's going to happen? If I look at the samples that I'm going to get, so this is time. So if I put time here, so 0, this is t seconds, 2t seconds, and 3t seconds, and so on. So at 0, at t, at 2t, at 3t. And I'm going to see what value I'm going to get from the first signal and what value I'm going to get from the second signal. So what I'm going to get, this is E1, and the second signal is E2. What value am I going to get from the first signal and the second signal? Let's assume this is equal to a 1. When t is equal to 0, I'm going to get a sample here from the first signal, that's 1, and from the second signal, that is 1. When t is equal, when time is equal to t, when I take the sample at t seconds, both of these are going to be 0, 0. When t is equal to 2t, I'm going to get negative 1 and negative 1. When I am at 3t, I'm going to go back to getting 0, 0. Now what do I notice here? If I gave you the samples, if you look at the samples, you're not going to be able, both of these samples that I obtained from E1 and from E2 are the same. So therefore, I have no way of differentiating E1 from E3, from E2. Okay, so therefore, so from here, we observe that the high frequency sinusoid produces the same samples or sample values as the low frequency sinusoid, and therefore this effect is called aliasing. Okay, is that clear? Now of course, if you remember, or you might have seen this sampling and you might have seen it result, or to get rid of this aliasing, is we have to apply the Nyquist theorem, which means we have to select my sampling frequency. The sampling frequency or the sampling time that I have to choose is related to how fast the signal is, the frequency content of the signal. So for faster signals, I'm going to have to sample at a higher rate. For slower signals, I can sample at lower rate. Nevertheless, always the sampling period or the sampling time is related to how fast the signal is. And since have two signals that are different speed, one of them is 3 times the frequency of the other, if I do not choose the sampling frequency or the sampling period correctly, I can end up with this effect that is called aliasing. Okay, we're going to look back at this aliasing later on when we look at the start transform. Okay, I'm going to stop at this topic, and then we'll have in the next module we'll look at the digital to analog conversion.